Welcome back to the Solutions Manual. In this video, we will solve the problem 8-3 from RC Hibbeler Engineering Statics 14th edition. According to this problem, the mine car and its contents have a total mass of 6 megagrams and a center of gravity at G. If the coefficient of static friction between the wheels and the tracks is 0.4 when the wheels are locked, we have to find the normal force acting on the front wheels at B and the rear wheels at A when the brakes at both A and B are locked, and we have to conclude whether the car moves or not. So to solve this problem, first of all we have to draw the free body diagram. So at point A we have a normal force and we also have a frictional force. Since this 10 kilonewtons external force is pulling to the left, so the frictional force would be towards right to oppose the relative motion. Similarly, for the point B, we have a normal force at point B and we also have a frictional force towards right to oppose the relative motion, and we also have the weight force acting in the downward direction. Let's label them. This is the weight force, let's call this W. This is the normal force at point A and this is the frictional force at point A. Similarly, this is the normal force at point B and this is the frictional force at point B. So this is our free body diagram. Now we can use our equations of equilibrium to determine the normal forces at point A and B. So my first equation is summation of moments at point A equals to 0. I am considering counterclockwise direction as positive. Since the line of action of FA and NA is passing through the point A, so these two forces do not have any momentum with respect to the point A. So NA and FA will not produce any moment about the point A. But this weight force is trying to rotate the car in counterclockwise direction about the point A, so the moment produced by this weight of the car will be taken as positive. So we have W and the momentum is this distance, which is 1.5 meters minus 0.6 meters, so 0.9 meters. Similarly, the line of action of FB force is also passing through the point A. So FB force does not have any momentum with respect to the point A. So FB force will not produce any moment about the point A. This normal reaction at point B is trying to rotate the car in clockwise direction about the point A. So the moment produced by this NB force will be taken as negative. So we have negative NB and the momentum is 1.5 meters. This 10 kilonewtons external force is also trying to rotate the car in counterclockwise direction about the point A, so the moment produced by this 10 kilonewton force will be taken as positive. So we have 10 kilonewtons and we have to convert this kilonewtons into newtons. So multiplying it by 1000 and the momentum is 0.9 plus this distance, which is equal to the radius of the wheels, which is 0.15 meters. So 0.9 plus 0.15 equals to 0. So if we substitute the known values, we would have weight is mass into 9.81 and the mass is 6 megagrams. So we have to convert it into kilograms. 6 exponent 6 divided by 1000 into 9.81 into 0.9 minus 1.5 NB plus 10 exponent 3 into 1.05 equals to 0. Upon simplification, NB force comes out to be 42,316 newtons. So this is our first answer. Now for the support reaction Na, we can do summation of forces in y direction equals to 0. I am considering up direction as positive. So we have NB minus the weight force plus Na equals to 0. So NB is 42,316 minus the weight force, and the weight is mass into the 9.81. This is the mass, 6 exponent 6 divided by 1000 into 9.81 plus Na equals to 0. So upon simplification, the support reaction Na comes out to be 16,544 newtons. So this is our second answer. So far we have solved half of our problem. We have determined the normal forces acting on the wheels at B and A. Now we have to conclude. So let me write a statement here. When both wheels are locked, so we can find the maximum friction at point A, which can be written as the coefficient of static friction into the normal force Na. So coefficient of static friction is 0.4 and the Na is 16,544 newtons. So the frictional force at point A comes out to be 6,617.6 newtons. Similarly, we have to do the same for the frictional force at the wheels B. So we have 0.4 into NB, which is 42,316 newtons. So the frictional force on the wheels B comes out to be 16,926.4 newtons. So these are our frictional forces, maximum frictional forces, when the both wheels are locked. So for the final step, if we compare the 10 kilonewtons pulling force and frictional forces at wheels A and B, then the frictional force Fa max plus Fb max is clearly greater than 10 kilonewtons, which is 10,000 newtons. Because Fa max is 6,617.6 newtons and Fb max is 16,926.4 newtons. So if you add them together, they become 23,544 newtons, which is greater than 10,000 newtons. So based on this, our conclusion would be mine car does not move. Because the combined frictional force at A and B is greater than the external pulling force of 10 kilonewtons. So this is our third answer. So this is it for this problem. I hope you would find this video helpful. If you do, please make sure to subscribe to this channel and also turn on the bell icon for the daily updates. And if you have any questions or any doubts in the free body diagram or in the equations of equilibrium or in the final conclusion, then feel free to ask in the comments section and I will try to answer them as soon as possible. Thank you.